Hello pre-calculus students, and welcome to a video on domain of rational and radical functions. First of all, I just want to point out something on these guided notes. Up here, this is the name of the file, and this represents the module. So we're in module 1 right now. This represents which day we've met in that module week. So we're in the second day, so this is the day of the week. And then this represents whether it's, the A's are always done in class, the B's are generally done at home, and they're not done, there's no live session to go with it. So this is in class or home. Okay, so the goal of this, this video is to help you understand the domain of a function from an equation with a focus on two specific kinds of domain restrictions that we're going to be looking at. And they correspond with some graphs that you should have just looked at on Desmos, that they're both radical. They both have a radical sign, so like example A here, or they have a denominator like example B here. Okay, now anything else we're not going to worry about right now, except I'm just going to have you at least explore this part C. But let me just kind of go over this with you. So polynomial functions, polynomials mean just a function to the degree. There's no root, there's no denominator, there's no log, there's nothing else except nth degree terms like x to the 4th or 3x to the 5th. And there's no negative roots because that would put something in the denominator. So that's what I mean when I say polynomial functions. And so if you look at the parent functions, and this, by the way, is a page you're going to get to know and review actually after class today. And this here's a 0 degree, 1st degree, and 2nd degree polynomial functions right here. And we go as far as the 3rd degree polynomial function. This is the parent function right here. Now it turns out that any way that we start out with the highest degree of 3, we're going to get something that's like this wavy kind of curve, like what you're seeing there. So let me see if I can. So here's a page from chapter 4 in your textbook. This is page 188, and all these pictured here, these are all polynomial functions. So you can kind of see what I'm talking about a little bit. They're all like these wavy. They're not always symmetrical, like as you see here, but there's no gaps, there's no asymptotes, there's no holes in them. They don't start and stop someplace. They continue forever. They all have arrows going in both directions, and they all approach positive and negative infinity. So all polynomial functions, also some of the other parent functions like the cube root function, you can see that has no restrictions on the domain. The square root function definitely does. The absolute value function has no restrictions on the domain, and the step function, which we're going to cover a little bit later in the first module, in the first unit, that also has no restrictions on the domain. You can see that even like wherever there's a hole in one, there's a point filled in the other, but there's no restrictions there. They're all x values are defined for the greatest integer function. But the two that we're focusing on right now, reciprocal function, square root function. Okay, and those are the ones that I had you graph for the warm-up. Okay, so for all these other functions though, the domain is simple. It's everything, all real numbers. That's supposed to be in R, all real numbers. Okay, when we get to these 3 different cases, I would like you to take just a minute, and all I'm asking you to do is find one value that would make this undefined over real numbers. Now, we're not talking about imaginary numbers here, just real numbers. So I want you to try to find one value that makes this not work. Okay, here's my thoughts and my examples. I picked 0 for A because if x equals 0, then you would get the square root of negative 5, which is not defined as a real number. And remember, we're talking about real numbers here. For B, I picked the only thing that I could, and basically the way I found that is I said, well, I know that this denominator can't be 0, so if I say 2x plus 3 equals 0, that number for x that solves that equation, that's not allowed. That's going to be a 0 in the denominator. So if you solve that, subtract 3 divided by 2, that's where you get the negative 3/2. Okay? And then for the last one, if you remember about logs, that if we set this equal to y, then the log of x equals y means that 10 to the y equals x. And you can't raise 10 to a power and get a negative output. So there's no way that the input of the log could possibly be a negative number. So any negative number would have been correct for part C. And by the way, for part A, any number that would make x minus 5 negative would be fine for the answer. So any number that you picked where x is less than 5 would work. I picked 0, you could have picked 4, and that would have worked. You could have picked negative 10, that would have worked. So you have a lot of possibilities there. Okay, so there's basically two rules that I kind of hinted at in examples A and B. And the rule is that if you have a radical function, so anytime you have a radical, the radicand must be greater than or equal to 0. So the radicand must be greater than or equal to 0. That's the only thing that's defined. So not defined would be a negative radicand, right? A radicand that's less than 0. Okay. For rational functions, the only rule really is that the denominator can't be 0. So anything that makes the denominator 0 would be undefined. So anything that makes it 0, so if the denominator, I'm going to say not if, I'm going to say this way. So any value making a denominator equal to 0 must be excluded from the domain. It's just not in the domain. So we have to, when we're looking for the domain, we have to mention that those numbers, usually there's just 1 or 2, those numbers are excluded from the domain. The radical is very different because there's not just 1 or 2 values, there's an infinite number of values. Going along with this, you graphed a bunch of graphs on Desmos, and I just want to kind of point out, if you look at the square root function, whether it's just the square root of x, square root of x minus 4, which just moves that over 4 units to the right, or a reflection horizontally of the square root of x, each one of these has a starting point. They have this end point, and that's really what makes this so important. This end point right here, and all radicals have an end point. And so when you look at that in terms of your graphs with radicals, they're going to have inequalities. It's going to be this statement right here says that everything, there's an endpoint at 0. Okay, up here there's an endpoint at 5, right? Well, there's a hole at 5 because this is, let's see, did I do this right? As long as x is, so if x is equal to 0, so I just picked the one value there. I didn't really write it out as an inequality yet. We're going to do that next. So when we have fractions like in example A, we're just going to take single points out. In this case, there's 2 denominators, so we're going to take 2 points out. So we're going to make the denominator equal to 0 and exclude those values. Okay, so the first case would be x minus 2 equals 0. So I'm going to say exclude these. So exclude x minus 2 equals 0 or x equals 2. Okay, also exclude x plus 3 equals 0 or x equals negative 3. So the domain is everything except for 2. X cannot be 2. X cannot be negative 3. So what we have here is, if we're going to just kind of look at this real quick, our domain would have negative 3 and 2. And it can't be either one of those points. Well, that was weird. Let's do it this way. can't be either one of those points. So those are the only holes. Everything else is good to go. So we're looking at 3 different intervals that we would write in our answer. And that's the way that we exclude those values. So we'd have negative infinity to negative 3, union negative 3 to 2, union with 2 to infinity. Okay. Next one is a polynomial. Remember, if we don't see one of these two things here, if we don't see a radical and we don't see a denominator or a rational function, then the domain is simply all real numbers. So this is the answer to the first one. The second one is just simply all real numbers. In the case where we have a radical, we're going to set the radicand greater than or equal to 0. The radicand is the stuff inside, so we're going to do 3 minus 2x is greater than or equal to 0, and this is the domain. This is not an exclusion, this is the actual domain. Now we can solve this in a couple of ways. This is just solving an inequality. I choose to add 2x to both sides. 3 is greater than or equal to 2x. I don't like to have to remember to divide by a negative and switch the direction. Now I'm going to divide, so I have 3 over 2 is greater than or equal to x. And in interval notation, that's x is less than 3 over 2, so I don't have to put the graph down. I'm just going to put the interval from negative infinity to 3 over 2. And oops, that includes 3 over 2, doesn't it? It doesn't include negative infinity. All right, the fun ones are when there's something more. So there's both of them in there. There's both a radical and a denominator. So we've got to think about this a little bit more carefully. So I'm going to let you try to do this. I'm going to find the exclusion because the square root of x plus 4, which is the denominator, can't be 0, and the restriction that the stuff inside of the radical x plus 4 must be greater than, can be 0. Square root of 0 is 0. So I want to see if you can put those two things together. Okay, so we got two things that almost seem like they contradict each other, but they don't. Okay, one of them says x cannot be negative 4. The other one says x must be greater than or equal to negative 4. And they have to both be true. Now notice I said and, they have to both be true. It has to be one and the other. Really, that's the way I should say it. So x cannot be equal to negative 4 and x must be greater than or equal to negative 4. So that means we can't count negative 4 and have them both be true. That would make this one meaningless. And think about it also. If you did put negative 4 into this original expression, you would get a 0 in the denominator. So x cannot be negative 4. So we want to make sure, and this is very important, that you have an open interval for that endpoint and don't include the endpoint. Okay? Why don't you guys try the same thing with the next example. There's two ways to break it up. There's two things you need to look at, and then we'll talk about it. Okay, so here's our answer. And here's the graph of the answer, the number line right above it. So we have to exclude the one value that would make the denominator 0. That's when x minus 10 is 0. So we exclude 10. We have to restrict that radical, so x minus 8 must be greater than or equal to 0, or x is greater than or equal to 8. And so just like we did before in example in D here, we put the circle here, and we're not going to fill in the circle because that would be saying, you know, they're not both true. So we can't fill in those circles. So we're always going to start by graphing exclusions. It makes things a little bit easier. It's consistent. It will never fail you if you graph the exclusions and you never fill those in when you're looking for the domain in problems like these. Okay, so we graphed the exclusion at 10, and then I graphed x is greater than 8, and I noticed that there's two intervals, and I stated both intervals, and there you go. All right, I hope this was helpful.